All right. Here we go. Boom, boom. Dun, 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 dun. Welcome, everyone. Office hours. Today was my first day of teaching at UCLA this summer. We're doing a cool summer course, Physics 1B. I think I had about 60, 70 people show up today. I think there's over 100 in my class, but it's always the first day. People are trying to figure out like where stuff is and how to log on and things. A lot of today's first lesson was just a bunch of admin stuff, basically. But, yep, it's about to be a busy next 6 weeks. Because every day, for about an hour and 15 minutes, I'm teaching electrostatics and like either like waves or sound or music or something. Except, interestingly enough, a lot of these Fridays are either going to be some sort of holiday, or it's going to be like an exam day, or one of the Fridays I'm traveling. So, actually, I think like 4 out of the 6 Fridays aren't even like going to have lectures. So it's kind of like really Monday through Thursday. It's kind of nice. Anyways, I'm trying a new thing here because one thing that I know the students kind of wanted for my office hours the last year I taught this is they wanted an easy way to be able to, I guess, like join like a voice call, kind of like Zoom and stuff. So what I'm going to do for, I think like the first hour here of office hours is I'm going to have a Google Hangouts. That's what this new thing here that you see, like there's a new chat thing here. There's a Google Hangouts link that I'm going to have them that they can join. So they don't have to go through Discord because, I don't know, asking a bunch of UCLA students to join Discord and then dealing with all the shenanigans that go on Discord is kind of a lot sometimes. So I'm going to allow them to just try to go in through this like Google Hangouts link. We'll see if they use it. It is only the first day class. I know a lot of people probably haven't really come up with questions they need yet for things, but we're here. Let me think. Any news from like stuff we're doing in the server? Oh, we had a chess tournament on Saturday. Super fun. Dr. Devious ended up winning. Played very well. But Maven did pretty good too. And then who else was there? Justin, I think, as well. And I played. Someone else played. No, I think it was just the 4 of us. Imagine failing before you started because you're using Google's tools. I love Google's tools, dude. What are you saying, man? Google's great. What's up, UA? UA found a way to join. Nice. Welcome to Office Hours, UA.
Oh, hi, Professor G.
There, how you going? How's it going, UA? Good to hear from you.
How are you?
I'm great.
I have some UI issue of
Yes.
coding since my earliest homework due is April 12th. And,
April 12th? Oh dear.
Yeah.
Wait, what? That's wrong. It should be due April 12th.
Yeah, and I don't have the pre-lecture question.
All right, let's help you out. Let me see. Let me load up my version of Kudu real quick.
Thank you.
See what we got. Wait. Is this it? What course is this? Signed in as authenticated user. Uh-oh. Uh-oh, what's happening? Wait a minute. Also, that's not loading for some reason. One sec. Web browser. English TV lessons. There we go. Okay, wait. That's going. Okay. So good question here. Because I think they might be updating stuff right now then. Because, wait, these are not even my courses. Wow, this is a different email. Wait, what the hell? What the hell? The helly? Loafers? No, sign out. Okay, one second. Let me do it this way. Yes, okay, that works. Sec. Oh. Let's see if I remember what my password is for this. No, one sec. Geo actual education. There we go. Okay, cool. All right, now I think this is loading. Okay, now I can see my course. That was super weird. I was logged in on like something else. Okay. Do you see Physics 1B? Like here, is this the course you see?
Yeah.
Okay. And then on the right here, you should see stuff that says like due soon. You're saying it says April for you?
Yeah, I saw for this part is no upcoming assignments.
Weird. Okay, let's make sure you're in the right class.
I'm in Physics 1B Lecture 3 S26.
Oh, fascinating. One sec. You are somehow okay. One sec. That's from the spring quarter. How did you get in that class?
Yeah, I feel weird since I can't see the answer for.
Yeah, well, that's a different class. So let me see. Is this the class you see? Physics 1B Lecture 3 S26. Yeah.
Exactly.
This is Kusenko's class from Did you take 1B in the spring quarter of this year? No? Wait, how the hell did you get in this class?
No, I just use the code posted on Canvas.
Oh, fascinating. What was the course on Canvas? Okay, one sec. Let me look on Canvas what I have. Maybe I put the wrong code. I don't think I did. One sec. Got a login. Great. Okay. Let's see. So on Canvas, you mean on wait, this is my old course. Sorry. This is it. Okay. So within here, you should have seen the code, right? QQ, or what does it say? GG? Yeah, QQIE9U.
Yeah, I saw that.
Okay. And so when you click on this link right here, for this course right here, does it still take you to the spring 26 one? Here, let me dump this link for you real quick. I'll put it in the chat here for you.
Yeah, I clicked the link and still put me to Physics 1B Lecture 3 Spring 26.
Wow! That's messed up. That's super messed up. Okay. Well, this is what I talk about, that they changed the whole back end and everything on it this last week. Okay, but that's like super screwed up. Okay. Here, do you want to, let me see. Which, okay, somebody said, am I pronouncing it right? Is it Yue? Yue Lu?
Yeah.
Okay, great. Okay. I had a friend named Yue at one point. Okay. Let me send an email to the Kudu people saying that you're not in the right class. Because when you see your class, you see this one, I guess. So, what does the URL say at the top when it says kudu.com/app/courses?
Yeah.
Does it say what's after courses / what? What's the what are
Nothing. Just
it just says just /courses, and it automatically brings you to that one.
Yeah,
wow.
And I also tried. There's a button shows I add a course, and I click that. Enter course ID is due the Physics 1B Lecture 3 Spring 26.
So when you put add course and you still put this QQIE9U, it still brings you to the spring 26?
Yeah.
Oh no.
Oh man, that's a huge technical issue. That's terrible. Okay. Let me write an email real quick. I'm gonna do it right now. I'm gonna write an email to the dev. I'm gonna tell them, fix this shit, dude. What? I can't have students in the wrong class. Yeah, because then how are you gonna do the assignments? It's okay. Also, don't worry about anything this first week is kind of like growing pains and stuff. You're not gonna get penalized with grades or anything, but I understand we want to at least get you on the right path with things.
Okay,
right,
got it.
let me write an email. Be like, student in wrong class bug. Okay, send me a hi Warren. I have a student who used code from the code and link for my physics. Let me just get the link for this. That's super weird that happened. I've never. This is what happens when they recode things, though. Okay. Course. Let me get the ID. Seeing Alex's old spring quarter. Let me see which one that was. That's this one. Okay, with ID. And then let me see. Pull this up. You know what's funny? I wonder if I go and like look at the grades. I wonder if you show up on that grade book. Oh, yeah, wait one sec. I'm curious. Okay, there we go. Yeah, crazy. Yeah, you show up on the grade book for the class from last quarter, but it shows you have 0 points because obviously you haven't done anything. Okay. Okay, I sent an email to them. They'll get that fixed, hopefully today or tomorrow. I mean, I guess the advantage is you can technically see all the stuff for Alex's course, which is a little bit different than my course. My course is a little bit different, but at least still all the material is there. But that's kind of a pain because you can't do the pre-lecture stuff because you're not in the right thing yet, right?
Yeah.
Yeah. It's like,
Emotional.
God damn it! Why doesn't it work? I totally understand. Okay, you're totally cool. You're totally good, Yue. I sent an email. It should get fixed hopefully today, if not tomorrow. If not, do not worry. I'll make whatever extensions and stuff so that you can still get all the grades for things.
Got it. Thank you.
Cool. You're very welcome.
And since I'm a transfer student and my previous course equivalent to Physics 1A is much easier than the course at UCLA. So I'm wondering if there are any YouTube videos or specific topic that can catch up.
Sure. Yeah, on stuff. So yeah, luckily I think the only thing you really need from Physics 1A to do Physics 1B is gonna be like some light kinematics. Did you ever do like 1D and like 2D motion in your 1A equivalent?
Yeah, just a little bit, very easy stuff.
Okay. So stuff where like, I don't know, you have like a ball and it like does something like this and then like it hits somewhere. That's like probably the hardest thing from 1A that you need to do in 1B.
Okay.
I have some videos myself I've made on them if you ever want to like look at them. Let me find them. Let me think. I put them on YouTube. And then let me look at my channel. Where's my account? There it is. And then we'll do, I think it was a projectile motion. Yeah, here we go. And I want the full one. Here we go, okay. How to do... Okay. So I think like 2D projectile motion is probably the thing you'll need. So
Okay.
I'll post the link here in the chat so you can see it. That's one of the 2D projectile motion videos I created. That should kind of help with it. And then, see if I have any other ones real quick. Yeah, that one was that. Where's the 2D projectile motion, like the complete one? I did it. 2D. One sec. Okay. And then this one. Yeah, this one's also useful. So those are both videos on kind of like 2D projectile motion,
Then you saw.
which I know is something that will come up on some of the 1B questions that's related to 1A. The other like kind of free way to learn physics. Have you ever heard of OpenStax before?
Yeah.
Yeah. So OpenStax has a really good, and I would say a lot of the Kudu material is actually based on it. So OpenStax physics. So if you go to like university physics, it's probably volume 1. I think, let me see. Volume 1 covers mechanics, sound, well, we don't need, well, that's what we're doing. Okay. Sound, oscillations, and waves. Where's just the, let me see. Subjects, science. There's physics. There we go. College physics, university physics. Maybe it is this one. Okay, cool. Then yeah. Yeah, university physics 1, I would say has good stuff. I mean, you want to be comfortable with like how to use, do you know about vectors? Have you done things with vectors before?
Yes.
Yes, okay, good. So like vectors are very useful. And then here, right, chapter 3 is some like basic 1D motion. Chapter 4 is 2D motion. I'm trying to think what else. We will do things with force diagrams for sure. Have you done like, you know, force of gravity points this way, this points this way, what's like the net force?
Yeah, a little bit.
Okay, good. All right, so stuff like that is important. So that's that would be like chapter 5 here, Newton's laws of motions. Here, I'll paste this link in here for you as well, Yue.
Okay, thank you.
But yeah, I would say, and then some of the conservation of energy stuff is cool. It's definitely useful. We're not going to have to do much rotational motion, I don't think. Yeah. And if we do, it might be like 1 or 2 little quick things.
Okay.
But yeah, that would, yeah, basically all of unit 1 is what I would say is probably the most useful thing for this. But cool. Where'd you transfer from? Where you coming from?
Santa Monica College.
Oh, SMC. I love SMC. I obviously, I live very close to SMC. I live on like Sawtell, so. I've taught a lot of students at SMC, like privately. I've done like private tutoring for kids at SMC before, so. It's a great transfer school. It's a great way to get into UCLA. I have a lot of students that have done it, where you go to SMC, you make sure you can do well there, and then you get whatever the required courses are, and then they bounce you straight over.
Yeah.
Yeah.
Okay, that's Oh, I have one more question since.
As many questions you want.
Tomorrow I will fly from Los Angeles to Shanghai, so
Wow.
for clicker question, I
Yeah.
might miss it.
Oh, that's okay. I mean, you might not even have an account, honestly. That works. So, right? Oh, wait. Were you the one that... Did you just email me? Sorry, I saw some email about someone having a third... Okay.
Emailed you earlier today.
Okay, you're totally fine. Yeah, don't worry. Yeah. Totally cool. Yeah, if you can't do it, it's okay. We want to make sure you have an account that works first anyways. So, yeah, just stay in contact with email and... or if you ever want to hop on here, that's fine. And we'll make sure you get credit and grades for that.
Okay, thank you.
Okay, you're very welcome, Yue.
Yeah, have a nice day.
You too. Enjoy. Boom, 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 boom. Nice. Okay, so like the office hours thing works now. People can like drop in, even if the website apparently for my textbook doesn't work.
Oh no.
Like what? Oh, Sensation's making jokes. Lonely, I am watching the World Cup. I do like the World Cup. I think the World Cup's great. Is France playing right now? I think I saw you submitted some questions, by the way. Let's see. What we got. Ooh, okay. Yeah, this looks like something we could do. Yeah, let's do this. It's France versus Iraq right now? Oh, let's see. Sensation, dude. The World Cup is great, dude. What's wrong with the World Cup? France is up 2-0. Wow. So here's the question, dude. Is Mbappe or Messi going to take the record for the most World Cup goals? Because they keep, like, passing each other, right? Like, France will play, Mbappe will get a bunch of goals, and he'll be number one. But then I think Messi got, like, 2 today as well. So they keep like, jumping each other. Having a professor who uses a soundboard is wild. Yeah. Don't worry, Brasicles. I'll open the Discord up in like 40 minutes. I want to keep the first hour where I'm like officially at UCLA with like some minimal shenanigans on Discord, and then after that we're off the clock. Whatever. Then I'll open the Discord and you guys can shit post or talk about whatever you want. But my job is technically to still help UCLA kids during that 5 to 6 hour. So, but this sounds like a good time if you like dudes. This is why That's why we can't stream office hours on the Discord for the first hour. Because otherwise I'm gonna get yelled at. I don't know if Sensation watches sports, but hey, England's playing tomorrow at 1 o'clock against Ghana. That's fun. Oh wait, France just scored again. It's now 3-0. Whoa. Wow. What's this guy? Dembele. Yeah, Dembele. I don't know if I'm pronouncing that right, but yeah, he's another really good French team. Was it Les Bleus? Iraq is happy to be there. Yeah, damn. Yeah, 3-0. Wow. They did have 2 shots, at least. That's pretty cool. 4 fouls, though. Sensation. Yeah, okay, cool. Yeah, I like the World Cup, honestly. It's been quite fun to I don't know, the whole... Oh, thanks for the follow, Ducky. I feel like the whole world like kind of comes together with the World Cup because everyone's watching it. It's fun. It kind of restores a little bit of my faith in humanity because
the world as a whole is like doing an activity. Only because I hate the French. Dude, so funny, Breasticles. It's holding your message for race, ethnicity, or religion. Dude, what? No, I'll accept it. Yeah, there you go. Yeah, accept it. Yeah, it's a common joke to hate the French. Don't worry. I have many French friends. And they also agree that most people hate them. Automod cooked me there. Sensation Black
added the permitted term, I hate the French. Oh, it's too good. What's up, Ducky? Okay. Yeah. My voice is slowly getting better. I keep, that's the other problem. I keep yelling at all these games, and I don't ever give my voice like time to like recover. But here we go. Let's while I wait for one of the UCLA students to submit some stuff, I said I would do other questions in the meantime. So let's do Lonely's here. Ihon papillon? What's that? I don't know. Are you having me say dirty things in French? Sensation. Alright, let's see. How do I screenshot things again? Oh, is that broken now? What the fuck? The hell? Oh, don't tell me snipping tool's broken now. I turn on sticky keys. Oh, man, really? Yeah, snipping tool. Well, that's what I usually use. I use snipping tool for everything, but for some reason that shortcut just stopped working just like right now. Super annoying. Whatever, we'll do it this way. We'll do it live. Okay. Let's pull this in. This was from Lonely. Snips. Okay. The graph of f of x is shown below using the same grid. Sketch an approximation of what the graph of f prime of x would look like. Ooh, I like that. This is great. Yeah, this is a really good question, Lonely. I like this one. So, whenever I see stuff like this, I also want to kind of mark what I call are like critical points, or like interesting points when things are changing, you know? Yeah, this is very red. Yeah, isn't it? Yeah. So here's what I'm going to do. Anywhere I see like something, so for instance, if it's going from like down to up, like that's something that's unique to me. I'm like, oh, that's doing something weird. Let's mark that as like an interesting time point. So I would like take this and I'll kind of like draw a dashed line to the same place. And then it looks like something's, changing here. So that's another interesting time point. Let's put one of those there as well. I do need to drink water, sensation. My throat. Yeah. The goon light on?
You done messed up, Aaron!
Okay. So this is probably another interesting time point here. My lamp is orange. And then it's flat, and it's flat, and it's flat for a while. And then something's happening here, and then whatever. Okay, cool. Alright. So, this is the graph of f of x. We want to look at what the graph of f prime of x is. The key thing here is that f prime of x is the slope of f of x. Okay? So, let's kind of like think. Oh, yeah, there's a bunch of sounds. Yeah, these don't come through Discord all the time. Yeah. Okay, so let's look at what's happening to the slope before this point, right? Slope is how steep something is. So it looks like, right, something here is like really steep and going down, yeah? And then it's getting like a little less steep, and then a lot less steep, and then eventually it has like a steepness of 0, right? It's like flat. So, permission to leave the ship to give the Covenant back their bomb. Okay, I'll put that on the ticker for you in a second. I don't know how to do it from here. Yeah, wait, where is my ticker? Okay, I'll find it later. Okay, so slope goes from being very negative to being almost 0. So if this was a graph of f prime of x, we know that before this time point, slope is very negative. So where would very negative be? Well, very negative would be down here, right? Right, this is like positive stuff, this is negative stuff. So it's going to go from being a negative slope here to like a less negative slope here to eventually having a flat or 0 slope here. Okay? And so we could kind of probably connect those lines and be like, okay, cool. This is probably what's happening to f prime of x when things go from negative infinity to what looks like here, I don't know, what would we say? It's like -4, a little bit before -4. Here we call this like -4. Okay. And then the slope starts increasing, right? So it's going to go from being 0 to being positive. But then the slope, goes from being positive to very positive to being less positive to being even less positive to again being flat. So I need a slope to go from 0 to like some positive value to then going back to being flat. Back to being 0. So that's that. And then from here to here, the slope is always horizontal, right? It's always flat. And that means that the slope is equal to 0. So from here to here, I can just say that this is just a bunch of zeros. And then right away, at this point, this is actually a discontinuity because it's going to go from being 0 to suddenly being positive. Do you see how like there's no curve here at all? It's just like a sharp point. Those sharp points are usually pretty bad. But a positive slope would be something up here. And then that positive slope stays the same. Do you see how it's the same steepness all the way from there? So that means the value of the derivative of f prime, which is the slope, is going to be the same, but be positive. Yeah, it's a jump discontinuity at 4. Correct. Correct, Breskels, yeah. Yeah. Yeah, so I think this will jump from being 0 to being positive. Yeah, cool. There you go. All right, yeah. So that's what I think it would look like. I don't think there's a curve. It's hard to see with the goon light on, Oh, at -4, you think I think, yeah, you're saying here. I think there's a curve. It's hard to tell. It could not have one, honestly, but it's kind of difficult to see from the screenshot we got sent. Or maybe you're right, actually. It's kind of hard, right? Is that a sharp point? I feel like there's some curvature there. I feel like there's some very slight curve. It's very tight, but I think there is curvature there. Whereas here, this is definitely a sharp point. I feel like we're doing one of those CSI Miami things where it's like enhance, 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 enhance. It's a tiny curve. Yeah, tiny curve. Yeah, exactly. Okay, cool. Okay, so hopefully that makes sense, yeah? But yeah, in general, how I always draw these graphs is I always try to line up, again, where interesting things are happening in terms of the slope. Like when it's going down or it's going up or when it's going flat. And then I just think about what happens in between those. Cool. Great. Good question, Randy.
Well done! Well done!
Nice. One sec. Cool. All right, let's download that one for you. That was lonely. We'll add it to you. That one took 8 minutes. Not too long. Looks like Lonely, you were also able to figure out the one, you posted this in our Discord, right? This one about the vectors. I hate this heading stuff. It's like south 20 degrees east. It's like, it's 20 degrees east of south. It's kind of backwards how they do it. And then you had heading, yeah. But you did the right thing here, Lonely, where you marked it as unsolved, because then our bot, literally, yeah, 5.5 hours later, went ahead and solved it. Yeah, okay. This is a cool, yeah, this is cool it did it right. Well, did it do it right, actually? That's a good question, actually. South 20 degrees east. So that's 20 degrees east of south. Does that make sense? It does. Okay, yeah. Usually cosine is for x and sine is for y, but when it's in this like goofy heading format, it actually flips. Here, if you want to see like why that is, let me just kind of show it to you real quick. Also, why did my snipping tool broke? You hate how AI formats stuff? I feel like this is pretty standard for like how it would happen, but yeah, maybe let's do this one. Let's just show you. Do you mean you just hate like Markdown? This is called Markdown. This like format. How it does like the heading and then it does this. I agree it doesn't show you much of a diagram, which is kind of annoying. But it is the right technique. So anyways, you have two vectors. One vector is the vector that the plane is like trying to go in. And the other vector is the vector of the wind that's going to shift it. And then you're going to get a resultant vector, which is where it actually goes. So they have the right idea here, which is okay. So let's call this like the blue vector here. And let's call this one like the red vector here. Okay. So south 20 east. So they're saying that you want to be 20 degrees east of south. So this right here is south, right? Pointing straight down. But then what happens is we don't want to be straight down. We want to be 20 degrees to the east of it. So instead of it being right here, they want it to go 20 degrees this way. So this would be, for instance, this amount is 20 degrees. And then it has a magnitude of 500. And then the other one is 60 degrees east of south. So south 60 east. So that's going to be something like this. But then this one's a lot less. They say this is only 60 kilometers per hour. So they're going to say that this here is 60 degrees. And then it has a magnitude of also 60. Okay. Okay, so when they want the resultant velocity, they just want you to add these two vectors together, which really means you take like one vector and you take the tail of it, or yeah, the tail of it, so the beginning of it, and you put it at the end of the other vector. So you could take this vector and attach it to the end of this one, and then this right here would be the resultant. Or you could take this vector and you could put it at the end of this one. Right? You see how you could take this, put it over here, and look, lo and behold, you still get the same resultant vector. So that's how you like add vectors, which is pretty cool. at least graphically. If you want to add them numerically, what you need to do is you need to break up this vector into its components. Because right now it points in both the up-down direction and the left-right direction. And we need to break it out into two separate parts. So just up-down and just left-right motion. And then add that to the up-down and the left-right motion of the other vector as well. So, for instance, this, if we wanted to break it up into components, you're going to have like this amount, and you're going to have this amount, okay? So, let's call this one like V1. And then let's call this one V2. So then, the components of this vector would be V1x, that's this part. And then this component would be V1y, okay? Now, the x component and the y component are perpendicular to each other, right? Like, left-right is always perpendicular, so it's exactly 90 degrees to up-down movement. So, taking this diagonal vector and decomposing it, like breaking it up into just vertical and horizontal components, is going to make a right triangle. Because the horizontal component is always 90 degrees to the vertical component. And so now, you should see something cool, right? You should be like, oh wow, look. This is a right triangle. Where this part right here is now the hypotenuse, okay? And if you know the hypotenuse, and you have a right triangle, and you know the angle, you know you can use trig functions, like sine and cosine and tangent and whatever, to find other sides. So, if we wanted to figure out the length of this side, right, the V1x, and this is our angle, right, this is now the opposite side to the angle. So, if we think about, remember, trig stuff, so, SOHCAHTOA, or here, I guess, yeah. So sine is opposite over hypotenuse, and then cosine is adjacent over hypotenuse, and then tangent's opposite over adjacent. So I always like to write it out this way. I'd be like, okay, well, the sine of 20 degrees, so the sine of this angle in this right triangle, that's the opposite side. So that's V1x over the hypotenuse. And the hypotenuse is 500. So then if I want to solve for V1x, all I have to do is just multiply this on this side. So you get that V1x is equal to 500 sine of 20 degrees. This is weird because usually when you're finding components like x components and y components, you're almost always using cosine for x. And the reason for that is usually when we're given angles for things, they're measured referenced to the x-axis. So in the case of vectors where the angle is measured to here, okay? Now the x component is the adjacent, right? Like if this is the angle, this side is the opposite. That's the vertical. And that is the opposite side to that angle. So this is why you usually use sine for y components and you usually use cosine for x components. But that's why you can't always memorize like sine is this one, cosine is this one, because it depends on what angle they give you. And this is a key example where the angle they give you here connects to the y-axis. And so now the x component is the opposite side to that angle. So sine 20 degrees is opposite of hypotenuse. So V1x is 500 sine 20. And that's what they said here. You see how here they said XA is 500 sine 20 degrees? Yeah, so this is V1x. Or here, let's do it the same color at least. And then so if you're trying to figure out V1y, okay, this is now the adjacent side to the 20 degrees. So you would say the cosine of 20 degrees, which is equal to the adjacent over the hypotenuse. So that's V1y over 500. That implies that v1y is equal to 500 cosine of 20 degrees. But then you have to be careful because this is pointing down. So you're going to want to put a negative sign on it, right? Usually we say like positive is to the right, left is negative, up is positive, down is negative. So that's why they put the negative here. What's up, Amir? So yeah, so that's why this is v1y. They put a minus sign, they use cosine, and then these are the numbers you get. Thank you, Amir. Appreciate it, dude. So yeah, that's how you break it into components. And, you know, kind of as a little cheat, anytime you figure out one component is either sine or cosine, the other one's the opposite. So in this case, x component was sine, so the y component's going to be cosine. I appreciate the Rosemary.
Good job.
Okay. So that's the components of the blue vector. It turns out we can use the same logic to figure out the components of the red one, right? And this is where ChatGPT is useful because it's just monotonous to like do these calculations. But it's the same thing. Hypotenuse is going to be 60. The angle is 60 degrees. So then we can say that V2x is now 60 sine 60. And then V2y is equal to negative 60 cosine 60 degrees. And then you get these two numbers. Now to find the resultant, right, which is adding these two together. Say something like that, right? This is the resultant. All you're going to do is you're going to add the x components from both the blue vector and the red vector, so from v1 and v2. So this would be like, let's say this, let's just call this like, let's call this VR. So this would be VRX, which is going to be the x component from v1, so v1x, plus the x component from v2. And that gets you the total x component for VR. And then you do the same thing for the y component of your resultant vector. Okay? So there you go. So then you have the new total x component and the new total y component for your resultant vector. But I think what they wanted was the resultant velocity, which means they want the magnitude of this thing, and they also want the direction. So once you have the final components, this is where you can just draw another graph. This is where it's kind of helpful to just draw another graph. And be like, okay, so what are the x components of my new resultant vector? Oh, well, it's 223 in that direction. So I can say, okay, cool. So we're going to do 223 this way. And then it's negative, basically 500 down. Okay, so then in the y direction, it's this way. Negative, let's just say negative, yeah, I'm going to say negative 500. Okay. And then so the resultant vector is this, okay? Now, this is another right triangle where we want to figure out the velocity is the magnitude, we want to find the magnitude of the velocity and also the direction. So the magnitude is the hypotenuse. And what you should remember, right, is that a squared plus b squared is equal to c squared. So if you rearrange this, you would get that, remember, this is a, this is b, this is c. You would get that c is equal to the square root of a squared plus b squared. And so that's why they do the square root of this 223 squared plus this negative 500 squared, but because it's squared, the minus sign goes away. And so this gives you the resultant vector, which is c, which is this, okay? So that's the length of this thing, and that's the resultant velocity. The next thing is to find the angle, which, yeah, there's two ways to do this. So a lot of times I would just figure out what this angle is and then know that you technically need this angle to do like the amount east of south, right? Because if this is south, you want the amount east of south. You could also do it this way, you could find out this angle, I guess. Which would... it's just a little bit more confusing to do it that way. So here, let's just do it my way. I would do this. I would find this angle. Okay. And the way to get that is to say, okay, cool. Well, tangent of my angle is equal to my opposite, which is going to be 500, over my adjacent, which is 223. Notice how I don't put the positives or the negatives in it either. Just strip all the positives and negatives from it, and then look at your diagram to know like where it's going. Because otherwise that can sometimes screw you up. Alright, let's go find my calculator. Where's my calculator? Here you are. One sec. Okay. And you want to make sure you're in degree mode for this? Okay, so mode, degree. And then we're going to do arctangent, so opposite in that case is 500 over the adjacent 223. And that's going to get me, ooh. That's a very, very small angle. Wait, what? Did we do this right? I should be. Am I getting 0.29, dude? What? I thought we were in degree mode. Oh! Haha! I made a mistake. You have to do arctangent, not tangent. Oh, dear.
Oh, no.
I hate when I make mistakes like that. Okay. Alright, here. Okay. Tangent of theta is equal to this. So if you're trying to get tangent... I totally blanked on this. It's the case of the Mondays for sure. You have to take the arctangent of both sides. Okay. Yeah, I can't believe I got that wrong. So arctangent of tangent of theta. These two things will cancel out. And you'll get theta is equal to the arctangent of 500 over 223. Yeah, that's what I meant to do. I was looking at my calculator. I was like, this is like so wrong. Okay. So arctangent 500 divided by 223. And that gets us, 60, let's say 66 degrees. Okay. But that's what this angle is, right? That's this. This is 66 degrees. When we want to do heading, right, we're measuring it, I guess, away from the south axis. So I really want this angle. So the cool thing here is, if I want this, right, this angle is equal to 90 minus 66, right? And that's where we get 24 degrees. So yeah, so then your final answer ends up being south 24 degrees east. This is like the heading. And there you go. Yeah. So that's your final answer. Cool. Good question.
Well done! Well done!
What's up, UC? So, does that make more sense to you, Lonely? How we did that one? Yes, cool. All right. Well, I posted that also in the Discord for you, so you can go see it. Cool. Coolio. Actually, I figured out why my snipping key isn't working. It's because my Windows key isn't working. Which, why is that? Sometimes these keyboards have like a gaming mode on it to like prevent you from accidentally hitting the Windows key while you're doing stuff. Let me figure out why that is. One sec. I want to do some Googling. Yeah, wait, my Alt key doesn't work either. What the hell? My Control key works though. Alt. Tab work? Yeah, okay, what? So all of a sudden my Alt and my System key don't work? Excuse me. Ugh, okay. Always something. Let's see. Alt and Windows. My Alt. See, ChatGPT will figure out. Yeah, okay. Yeah, I was looking for like a game mode. I don't want to restart Windows Explorer right now, though. I really don't want to do that. Let me see if I unplug my keyboard, plug it back in. Man, I should turn off sticky keys too. That's always the one that screws things up. No, it still doesn't work. What the hell? Or actually, my start button just doesn't even work. Weird. All right, one sec. Yusuf says, can you explain the concept of light polarization in regards for the I naught cosine squared? Sure. Oh, like what happens to the intensity? I know intensity is always like something squared, and then cosine like picks out the component that's in the same direction as it. So, and then I got, yeah. Yes. Let me. I know how the equation works, but yeah, you want to know like physically why it works. Alright, let me pull up some images. So why is my display not working these days? What the hell? What the hell? Why is it not doing? Dude, I'm having so many issues today with like PC stuff. Super annoying. Okay. Yeah, okay. So light, right? Light is like yeah, what's up, Obi? Thanks for rating, dude. Okay. So light is what we call electromagnetic radiation. What's up, famished? Potentially famished? Dr. Cole, what's going on, dude? Yeah, we're doing a little bit of this is I guess some light, like almost like I guess kind of like optics almost. Like waves? Yeah. Let's give a shout out to Obi though. Obi's great. Obi teaches a lot of like math and stuff over across the pond in the UK. So if you ever need help with like differential equations and stuff, Obi's gotcha. Anyway, so light is electromagnetic radiation. which has, we would say, like electric and magnetic fields. Let's get like a picture of that maybe. Reading about Claude being given a pre-calculus exam. How did it do? How did Claude do? Okay, and then it's been an hour, so here I'm gonna stop the. I'm gonna stop the one over there, and then maybe my Windows key still doesn't work. Here, and then I'll open the stage to you guys. Though I don't know. My PC's been hanging a lot today for some reason. Here, let's fix that. There we go. There we go. Okay, that should be working again. It's an obsequious bastard. It failed miserably. Really? I thought Claude's quite intelligent, honestly. How does Brewster's angle? Does Brewster's angle play a part in this? Maybe. We'll have to see. I gotta remember. Wait, is Brewster's angle like why the sky is blue? I feel like it is. Oh, okay. It's a specific angle of incidence in which light with a particular polarization is perfectly transmitted. Oh. Right, S versus P polarized. Point was he gave it a question that has not been seen before. I'm sure it has since been modified. Let me see. Yeah, so polarized has to do with like the angle. So light. Here, let me get like a picture of this. Or electromagnetic radiation, right? Looks like this, right? So, right, electric fields are always 90 degrees to the magnetic fields. But then, if we were to look at this head on, like if we were to look at it this way, you would end up seeing, let's say, like a circle. And you'd see that the electric field is polarized like up down, right? It's oscillating in the vertical direction, whereas the magnetic field would be oscillating in the horizontal direction, okay? So generally when we're talking about light, we only care about the electric field. Or I guess just by convention, it's just the one that we talk about when we talk about the polarization angle. So this we would say is polarized, I guess, at like 90 degrees, right? Or maybe 0. It depends like where you're measuring 0 from. If we're mathematicians, we measure 0 from here. Sometimes in physics, we measure 0 from here. So this would be like a single like beam of light. It turns out light is not like single beams, right? It's a bunch of light at a bunch of different wavelengths and at all sorts of like random polarizations. So most light is unpolarized because what happens is you actually have a bunch of these light waves kind of all on top of each other, and they're all at a bunch of different random angles, okay? Now the special thing is that when you run light through a polarizer, or like a polarizing filter, it only lets light of a certain direction to go through. Like, if you had, for instance, let's say this is like unpolarized light. So light that's in all different types of angles. Okay, so that would look like, stuff like this, right? It's all over the place. And then let's say you put it through a polarizer. Or like a polarizing lens, okay? And let's say that polarizing lens is just like this, okay? So it's like vertically polarized, okay? So in this case, only light or that has electric fields that are oscillating up and down are really allowed to pass through uninhibited. Anything else, like let's say for instance, let's say you had another beam of light. Let's make it like slightly less red. Like pink. Let's make it pink. Okay. Yeah, with a certain. Well, I don't know about probability. It's just how it is. So let's say, for instance, you had some light that was polarized, that originally had like this angle on it. Okay. And then this angle, right, is some angle theta, right? Okay. So the component of this electric field that's allowed to pass through the vertical polarizer, that would be this amount, right? Which would end up being, let's say this is like E2. So this amount would be like E2x, for instance, if this is like an angle. And that would be equal to E2 times the cosine of theta. So here, let's call this like E2 prime. So E2 is the original magnitude of the electric field that's coming in at this angle, referenced to what the polarization is of the filter. Then E2 prime is equal to E2 cosine theta. Do you see that, Yusuf? Do you see how only the x component, or not, whatever, the vertical component of E2, whatever, the component that lines up with the angle of the polarization, that is the only thing that like travels through. And so that ends up being E2 cosine theta. It's kind of also like a dot product, right? Right? Dot product measures like how much of one vector is in the direction of another vector. So you're measuring how much of your light is in the same direction as the polarization filter it's going through. And that's, dot products is like AB cosine theta. I guess sometimes they call this like the projection, right? That's what they call it, projection. So anyways, so the amount of, let's move this over. So now what happens, like after it's been gone through the polarizer, is now all of the light is going to be in the up-down direction. And this is now perfectly polarized light. This is completely polarized light, because all the light only oscillates back and forth in like one axis. Now, intensity, this goes as the electric field squared. So that's why we say that I is equal to your initial intensity times cosine squared of theta, right? Because the electric field goes as the electric field times cosine theta, so the intensity would go as cosine squared of the original intensity. I guess you could also write it this way. You could say like, oh, well, E2 prime squared over E2 squared is equal to cosine squared theta. Or actually, yeah, if you just take this and you square both sides. I'll show you. You get E2 prime squared is equal to E2 squared cosine squared theta. And then this right here is now like I2 prime is equal to I2 cosine squared theta. Yeah. So that's why intensity goes as the cosine squared of the angle between the polarization of your light and the polarizer that it's going through. In the case that you have unpolarized light going through a polarizer, you automatically lose half, is what happens. Yeah. So unpolarized to polarized, what that does is that turns, we would say like I is going to equal to 1/2 I naught. And you can think about it, like, so if your light is randomly polarized in all sorts of directions, then half of it is going to be up, down, right? The other half is left, right, which doesn't contribute at all. So that's why unpolarized light going into polarized light gets you half of what your initial intensity was. Cool. Okay. So hopefully that makes sense. You're asking about like Brewster's angle. So it looks like Brewster's angle they describe as, I wish this would work today. Why are we not working today? Let me turn this one off maybe. Oh, one sec. I gotta turn that one off. Okay, there we go. Yeah, okay, cool. Anyways, sorry. Brewster's angle has to do with when you have unpolarized light and it hits a surface. Is the angle of incidence which when a particular polarization is perfectly transmitted through a transparent surface with no reflection. When unpolarized light is incident on this angle, the light that is reflected from the surface is perfectly polarized. That's cool. So if you have unpolarized light that hits a surface at a certain angle, which is the Brewster angle, then the light that's reflected is perfectly polarized, which means it's all in one direction. That's cool. I guess there's an equation about it. I didn't know about this though. I thought it was related to, yeah. This is cool though. This is how, yeah, you're able to like, so like reflections on glass happen at certain like angles, just with how like sunlight reflects. And so if you have polarizers, you can actually cancel out all of that reflection. Yeah. Yeah, very cool. Yeah, so when like sunlight, for instance, bounces, I guess, off of reflective things like windows, the light that bounces out can be polarized at a certain angle. And then if your film, if your whatever your camera is, has a polarizing lens that's 90 degrees to that, you end up filtering out all that reflective light. This is also why like reflective polarized sunglasses are really cool. I guess there's also Brewster windows. Oh, cool. Nice. Okay. So hopefully that makes a little bit more sense with like Brewster's angle. Here, I'll let me download this for you. This was Yusuf. I think it's just physics. Okay, Yusuf. And then I'll post the screenshot for this if you want to see. It'll be in our Discord. Over... Discord wants to load today. Dude, none of my windows are grabbing today. What the hell? What the hell? Why is Discord not grabbing either now? Oh, man. Yeah, it makes sense. Nice. Cool. Sorry, all of my Explorer things decided to stop working today. Super annoying. Just right now, they just stopped deciding to work. Yeah, where's Discord video? There we go. Yeah, it should be on. It's not grabbing it either? The hell? Okay. I'll probably just have to reset. Oh, no, there it is. Okay, now I grabbed it. What the hell? Okay, anyways. So, yeah, here you go, Yusuf. I'll post a screenshot to that here. So, if you ever want to go watch it. And then the website, if you want to go join our Discord, actualofficehours.com. Well, if this wanted to load. There's a link here to join our Discord. And it's just that website, www.actualofficehours.com. So, check it out. Cool. Let's see. What was this? Ludwig Strassenhaus. Hello, I need help understanding how to do this problem. It says x squared plus 4x is equal to negative 3. How do I solve for x? Okay. Well, that's not too bad. First thing you always want to do, you want to put this in like standard form. So you always want like something like equal to 0. So you can move this over here, Ludwig. Just add 3 to both sides. And that gets you x squared plus 4x plus 3 is equal to 0. And then you can factor. You can factor here. Because this is a really nice quadratic. You could use the quadratic equation, but... yeah, I don't want to do that. Quadratic equation sucks. You don't use it if you don't have to. So what I like to say is I say, okay, well, what two things multiply to 3? All right, so like what times what is equal to 3? And what two things add up to 4? That's from here. And this should be pretty simple to see, right? You know, two numbers that multiply to 3. Well, there are not many numbers that multiply to 3. It's actually just 1 and 3. 3 is prime. So you can be like, oh, cool. Well, 1 times 3 is equal to 3. And also 1 plus 3 is equal to 4. Bingo. Amazing. Crazy. So that tells me that 1 and 3 are my factors. So then all you have to do is you can rewrite this as it's going to be like x plus factor in parentheses times x plus the other factor. So in that case, that's going to be x plus 1, x plus 3 is now this whole thing, but it's still equal to 0. Okay, so we still have to say equal to 0. And now to solve for this is really fun. All you need to know is I could say, okay, what x makes this equal to 0? Or what makes this equal to 0? Because if either of these things are 0,
My man.
then the whole thing equals 0. And so this should be pretty easy to see, right? Okay, so if x plus 1 is equal to 0, that tells me x is equal to negative 1. And then if x plus 3 is equal to 0, that tells me x is equal to negative 3. So then your solutions are x equals negative 1 or x equals negative 3. You could go plug these back in if you wanted to try. Just like double check yourself. Try plugging in 1. Or negative 1, sorry, right? Yeah, so this would be negative 1 squared plus 4 times negative 1. What's that? Well, this is 1 minus 4. That's negative 3. And then we could also try negative 3, right? So I could also do negative 3 squared plus 4 times negative 3. And this would end up being 9 minus 12, which is also equal to negative 3. So there you go. So, yeah, 1 and 3 are your factors. You could also say that -1 and -3 are your zeros. Because if this was a graph... What's up, 1K?
Good job.
So if you had, for instance, like y was equal to x squared plus 4x plus 3, this would look something probably like this, I'm guessing. Then these points right here, x equals -3, x equals -1, these are the zeros. These are also called like our zeros. Because it's where this is equal to 0. Where the y is equal to 0. Which is also, you know, where it crosses the x-axis. Also called the x-intercepts, I guess, right? Yeah. So anyways, that's how you do that one, Ludwig. Well, that helps. $1K, how's your summer going, dude? What's cracking? You going anywhere fun? Any vacations? You got it? Nice. Cool. And yeah, Ludwig, I'll put the screenshot of that also in our Discord. Which doesn't want to load today, but well, my Windows Explorer is having so many issues today.
Oh no. Oh no.
Oh wait, what? Why is this always this one?
Emotional, damn it!
There we go. It's like I'm having so many issues today with computer stuff. Oh man. All right, let's see what else we got. We got some other ones in the queue. So again, if you want to submit questions into our live queue, which doesn't want to load today, but okay, fine. There we go. Difficulty 9 out of 10. Oh dear. What did you do here? What is this question? Hi there, dude. What did you do? What are you doing here? This is like F equals IL cross B, right? But then the electric field is a decreasing exponential. Sorry, there I guess you guys can see it. Oh wait, yeah, and it's decreasing as a function of time. Oh. Dude, this is fascinating. So, is this where dB dt is going to equal like mu naught I? Let me think. No, that's the magnetic... Oh, wait. Change of magnetic flux is equal to EMF. Yes. dB dt is equal to EMF. And then from that, there needs to be some sort of resistance, right? To create a current? Oh. I think. Well, here, let's see which question gets picked. If your question gets picked, and then Breasticles has one, whoever's gets picked, I will try to do. I think it might be Lonely though, because Lonely has 256 votes. Okay, but let's just see. I just want to try.
Let's go gambling!
There you go, Lonely. Okay, and then I'll probably do either Hi There's or Breasticles. Oh my god, dude, why did your lamp change colors?
Oh no.
His lamp is blue now, dude. Nice, you're bringing a lot of physics questions? Please do. We'll be here to help with physics all summer. 3 times a week, maybe 4 times a week, honestly. You're taking physics in the summer? Nice. I'm teaching physics this summer, actually, 1K. I need my snipping tool to work. There you go. What physics are you taking, 1K, by the way? Which one? Oh, it's the same one? Already did it? Okay, cool. Okay, so whatever. We can just mark that when it's done. Okay, so it's kind of a toss-up between breasticles and hi there. Interesting to see how, because hi there's is a 9 out of 10, he only gets 30 votes per hour. Breasticles, you get 47 because yours is a difficulty 8. Oh, it's just high school physics? Cool. Okay. I can probably help with that for sure. Anyways, let's still choose a winner.
Let's go gambling!
Oh, it ends up being you high there, though. Okay. I don't know if I'll actually be able to do this one for you high there. I'm probably just going to like look at ChatGPT and try to explain it. I will say like what my intuition is. Let me write down things I think I understand that I could do this with, and then we'll see how it would actually work. Because, yeah, I see non-conducting cylinder. Okay, so you have a cylinder, a radius r, and a mass per unit length. Okay, so it's an infinite cylinder, technically. Okay, this is probably like a JEE question or something. Okay, and so mass per unit length is equal to like lambda. And then it carries a uniform surface charge density sorry, what is that? Is that sigma? Yes, sigma. And then there's a magnetic field. Okay, and this is the other key thing. It rotates around its z-axis, right? And you're saying that there's a magnetic field being applied in the z-hat direction that is decreasing as a function of time. Okay. So there is some B field. Right, that's doing this. And it's equal to some B naught and then e to the negative alpha t. So it's going to look something like this, right? This is BZ. Okay, cool. So magnetic field is decreasing through a non-conducting... Well, okay, non-conducting is interesting. Because some things I know. I know that F, so the force being applied on something, is equal to the current times the length crossed with the magnetic field. So that's the force being acted on like a loop, on like a thing of wire. I don't know if that works for non-conductors as well though. But also it requires you to have current, right? And the only way you can have current is if charge is moving. So because this is a conductor, the charges are kind of fixed. But if they start moving, that will like simulate a current, right? Because I see we talk about like the angular velocity induced by the changing magnetic field. So angular velocity means that this thing is going to start rotating, right? And if it's rotating, then technically you have like a bunch of charges here that are rotating, and that will create like a current. But man, it's a disk on the top. And then you also have all of this to worry about as well. Okay. And then the other thing I consider is, what is it? It's magnetic flux and EMF. I think it's d phi b dt. Yeah, it's Faraday's law. Faraday's law, right? Or I guess Lenz's law, but But this is also important. Anyways, the change in magnetic flux. And again, this isn't a coil, so I don't know how this works with non-conductors. Yeah, wait, these are all for conductors. How does this work for a non-conductor? I don't know that it does. Because, yeah, how can... You can't... I guess the only way you could create current is if it started rotating, right? So that's my other thing. So... I feel like... Okay, so it's... The magnetic field's pointing up, down. So the flux needs to be perpendicular to that, or needs to be parallel to the surface area vector, which is also up, down. So I believe, right, EMF in this case is going to be equal to pi r squared. All right, that's the area of this. Times dB dt. And that's just going to be equal to... What's up, Warren? Pi r squared, and then that's going to be negative alpha b naught e to the negative alpha t. But wait, now the derivative is also changing. It's a function. So wait, so the EMF is changing? Oh. I don't know about this. I don't know about this question, dude. It was given as a level 9 question, though. Let me throw this at chat. I just want to see how chat would do it. It's probably a tricky one.
I feel like it would be something like, what's his face? The first law you ever learned in electricity, Coulomb's law.
V equals IR?
Question. Yeah, something along the lines of Coulomb's law, I feel like. Sort of. Just because the current or the charge can't actually move.
Right? Yeah. But,
So
but
the
the thing
changing-
can move. The thing can rotate, right?
Yeah, because I guess the changing magnetic field would cause a change in the electric field, and then that charge internally would experience a force.
Yes.
But the
Right.
charge can't move, so
So the object has to move.
I feel like it would be something along those lines, but
Yeah.
not too
Or
sure.
you mean F is equal to QE V cross B?
Yeah,
Okay.
yeah. It's been a while since I've done any E&M.
Yeah, that's the other one. So F is equal to Q E plus V cross B. Or I think it's like this technically, right?
Yeah, I think
Yeah.
so.
Well, dude, ChatGPT is still like it's looking at radiation reaction. What the hell's was that actually a question? Oh,
I mean, it says
accounting.
to neglect it.
Oh, I see. Dude, that's crazy. Yeah, part B says to start. What class is this from, dude? All right, well let's see. Maybe Faraday's law here. So it says, for a circular loop at radius r, Faraday's law gives E dot dl is equal to negative dB dt. Okay, cool. So yeah, so there's a phi direction electric field that happens, right? From the pi r squared dB dt. Okay. And then since that's that, dB dt is that. So E phi is that. Okay. And then the charge per unit length on the surface is Q prime equal to 2 pi r. So then they go with like some torque here. Okay. I think I say what they're getting at. They're saying that So if you're looking down, so if this is the z-axis, that's no. Sure, at some location R, I get you get some E phi that's happening. Why is that E phi happening again? Sorry. Oh, from Faraday's law. E dot dl is, yeah. Where'd that one come from? Sorry. There we go. Changing magnetic flux induces an electric EMF field. Okay. Yeah, okay. Right. So I was kind of right about this, except this should have been E phi dot dl. That's what it should have been, instead of just EMF. And then that produces a torque because you have a perpendicular force to a radius, and that's gonna be equal to QE, which, yeah, you were right with breasticles. Just F equals QE. But man, dude, this charge per unit length on the surface, is that what they said? Sorry, what did they say here? It carries a uniform surface charge density, sigma. So, how do you say that the charge per unit length is sigma times 2 pi r? Because charge per unit area is equal to sigma. So the charge per unit length, they just multiply it by 2 pi r? I guess so. And the torque per unit length is that. Substitute E phi. Let the moment of inertia be I prime. Okay, because then torque is equal to I alpha. Sure. And then you integrate it from 0 to omega. Oh, okay. Integrating from rest. One sec. Oh, okay. Because at omega naught, that's right, t equals 0, omega is equal to 0. Okay. And then if the cylinder isn't as a solid uniform cylinder, then I is that. Wow. Oh, crazy. Okay, and then this just gets absolutely just nuts. Okay, cool question. Hi there. This is very advanced. It's cool that it involves a lot of mechanics, but this would be, I would say, upper division E&M. It's kind of just like a fun little challenge question, honestly. Right here. I'll count it as done. And I'll post the ChatGPT link to it as well, so you can see the solution. It said estimated grade level was 17. I don't think that's a graduate level question. Yeah, I don't think it's grad school. Definitely upper division undergrad though. But anyways, yeah, it was cool. I kind of understood some of the concepts, and breasticles understood them as well. Just the basic Coulomb stuff. But that's a cool application of where you have to understand a lot of mechanics in order to also do an E&M question. Because there's a lot of things there with torque, right? Moment of inertia. You had to do some integration and stuff. Yeah, Crazy. Okay. Let's see. I think there's only one other question in the queue, so it's probably gonna be you, Breasticles. Let's go see. Oh wait, did it not spin? No, you got
it's
picked.
fun for me.
Oh, okay, cool. You win. Okay, let's see what this one is. Variation of parameters. Okay, are we gonna do more eigenvalue stuff here?
Yes, yeah.
Is this from your summer class you're taking right now?
Yeah. I was looking for other problems, and then I didn't feel like.
You're like, wait a minute, we can just do my advanced. So this is a graduate level differential equations class, right?
Yeah. So
Right.
according Zach looked at some of the work, and he was like he said, looked more like his ODE theory class than he took than advanced FEQ, but that's just kind of like different like structures. I guess
That's his opinion on it.
classes, but yeah,
Okay.
yeah. This is from advanced FEQ.
Okay. Variation of parameters. Is this it's like the PDV thing you do or something? What is variation of parameters again?
It's go away. I'm checking out. Let me. I'm trying to add screenshots on the real quick to send you
Okay.
as well.
Yeah, it's where you try to turn it into like a product rule or something, right?
No, not quite.
Or there's a
It's,
Wronskian or something. Yeah, there's a Wronskian involved.
Yeah, no,
Yeah, okay, I remember this one.
It's a bit different since it's a system, but that's kind of our general formula in this case.
Okay.
So we just need to find
So
our
x is equal
phi
to
and
what's that? Phi t
yeah, 5t. It's a matrix.
times. Dude, your handwriting, bro.
Yeah, it's not very good.
Is that a
That's,
C? It's a C vector.
Yeah, the column vector of constants.
Okay, plus 5t, and then we're gonna say phi inverse of t, and this is an
Yep.
integral.
hmm
And then is that g vector?
That's f vector of t.
F vector of t dt. Wow. I remember, yeah, if we want to talk about like regular variation of parameters, I do remember it's like this. And you end up doing like some u1, right, is equal to yeah, okay, so you solve like the homogeneous way first, right?
Mhm.
And then you get like two parts, and then you do like u1 is the integral of the second part of the Wronskian of y1, y2, and then u2 is the Wronskian of the first one. Sorry, is the integral of the first one, Wronskian, and then I want to say the final answer is like, yeah, it's u1 y1 plus u2 y2. Yeah. That's the particular. Okay, this is a great little like short explanation of how to do it. Okay, but we're doing this as a system of equations now.
Yeah, and that's why that equation is the way it is. If you do the variation of parameters for a dx dt is equal to x, you get a very similar looking equation for that. But it's different in this case because it's a system, so we have matrices and vectors and all that.
Okay.
So we want to just start by finding the eigenvalues to start with.
Yeah, let's find some of this thing, of this one right here, of the top one.
Yeah.
Sorry, okay, let's do this. I can find eigenvalues.
My man.
I know how to do that. Okay, so step one is like find some eigens. So, you're gonna have negative lambda 2, negative 1, 3 minus lambda, and we're just trying to do the determinant of this is equal to 0, right?
Yeah.
Okay, so that's gonna be lambda times lambda minus 3 plus 2 is equal to 0. Okay. So lambda squared minus 3 lambda plus 2 equals 0. So you get lambda minus 1, lambda minus 2.
Yep.
So lambda equals 1 or 2.
Now we want to find our eigen vectors for that.
Okay, then we gotta find eigenvectors. So I think you plug in lambda is what you do. So okay,
Yeah,
so
you plug in lambda and solve that being equal to the 0 vector.
Okay. So -1, 2. Elliot says, thank you for the limiting reactants video. You're saving me for my test tomorrow. Nice. I'm glad you liked the video, Elliot. Yeah, that's the one with the cakes, the eggs, and the stuff. Yeah, that's a super fun video. I'm glad that one's getting some attention. I put a lot of time into that, and then like no one really watched it, but I'm glad it's helping you. 3 minus 1 is 2. I'm always like trying to figure out what the algorithm wants. Oh, this is actually pretty. This is pretty. Wow. Okay. So this is like times x1, x2. Oh, okay. So negative x1 plus 2x2 is equal to 0. So just x1 is equal to 2x2. So okay, you could just have 2 and 1. Is this an appropriate vector? I feel like it is.
Yeah.
It's not normalized.
That's correct.
Okay, cool. Okay, so for lambda equal to 2, so I get -2, 2, and then -1, -1, 1. Oh, okay. That's kind of the same thing, no?
Almost.
Almost. Okay, that times x1, x2. So then I get that -2x1 is equal to x2, and also negative x1.
2x.
Yeah, negative.
2x.
Sorry. Yeah, sorry. 2's on both. Yeah. Or negative x1 is equal to x2. Okay. So that could just be 1, -1.
No negative. It should just be because you would have.
Sorry.
Negative 2x.
Sorry. Plus is equal to 0. That's what I meant to say.
Yeah. Which means
fucked
that
up.
they're equal to each other.
Good. Yes. So x1 equals x2. Oh my lord, Goldie's problem is so difficult. I can't even rank its difficulty. What did you put in there, dude? I think I have something built into the here. Oh yeah, it couldn't even rank it. Non-Newtonian fluid satisfies an upper convected Maxwell dude, holy jargon, dude. What is this word vomit, dude? This is absolute word vomit. It's too funny. Okay. All right, so that one is just 1, 1 or 1, 1.
Yep.
Great. Okay. I can figure out eigenvalues and eigenvectors. A valuable thing to know.
Yes, you can.
I'm so
All
happy.
right, and then
Fuck, I do
from
with
here,
these
what
things.
we're gonna do is we're gonna define our matrix phi, and we're gonna call that 2 e to the t, e to the 2t, e to the t, e to the 2t.
So
And
2.
yeah, and then e to the 2t
Mm-hmm.
is top right, and then the
E to the
top
t.
left is 2 times e to the t.
Oh, okay. Wow, fascinating. Okay, well, let me write this a little bigger. Sorry. Okay. 2 e to the t, e to the 2t.
E to the t, and then
E to the t, and then 2,
2t.
and then just e to the 2t.
Yeah, and that just comes from the eigenvalues and the eigenvectors that we got. Because if you look at it,
Oh, I
on
see.
our-
1, 1,
our
and
first-
then 2, 1.
and then obviously our eigenvalues in this case are 1 and 2.
What about the minus sign shit happening here? Do we really care about that?
We'll get to that in a second. That's the
Okay.
the f of t that we use in the integral.
Okay.
And then we just want to take the determinant of this and make sure it's going to be non-zero.
Okay, so that's 2 e to the 3t minus e to the 3t, which is just equal to e to the 3t.
Yep.
Cool.
So we're good in that aspect because we need to find the inverse of it, and we can't find the inverse of it if the determinant's 0.
Oh, okay. Well, I remember how to find the
okay.
inverse, right? Inverse, you like, I feel like you switch these, and then you make one of these negative or something?
You'll switch them, and then you'll make both of them negative.
You don't change the top right and the bottom left?
No, top right and bottom left are negative, and then you swap the diagonals.
And then you swap diagonals. That's what it was, right? Okay. So this is e to the 2t. This is 2e to the t. Yeah, so we swap this one with this one, and then you make these negative. So then this is negative e to the t, and then this is negative e to the 2t, but then we multiply by 1 over the determinant. So that's 1 over e to the 3t, right?
Yep.
Does that make anything nice? Maybe. Do you want me to multiply it through?
Yeah, it helps you multiply it through.
Okay, so e to the 2t over e to the 3t is just e to the negative t. And then this is negative e to the negative t. And then this is negative e to the negative 2t. And then this is 2 e to the negative 2t.
Mm-hmm.
Cool. So that's phi inverse.
Yep. And then from there, what we can do is we can evaluate our integral.
Okay. So it's the integral of the inverse, and then what is f of t?
That's what's called our forcing term. So that's
Forcing
the
term.
Yeah, that's the non-homogeneous part. That e to the t negative e to the t.
Okay, so we would do the integral of this, and then this is called like the forcing term.
Yeah, we call that a lot the forcing term. Just whatever makes it non-homogeneous.
Little bastard. E to t, negative e to t. Okay. And this is still dt, right?
Mm-hmm.
Okay. How do you integrate a matrix?
Well, first you'll want to multiply your column vector through.
Okay.
Because that simplifies it a lot.
Which one was the column vector? Sorry.
Your e to the t, negative e to the t. You just multiply that to the matrix.
Oh! You're saying multiply this through on this. Oh,
Yeah.
okay, cool. Oh yeah, I got you. Oh, so
Because
I'm
what
gonna
that
get,
does is that turns it into a vector. Just a column
I see.
vector.
Because we have a 2 by 2 being multiplied by a 2 by 1. So that's gonna give me a 2 by 1.
Yeah.
Nice. Love that. Okay. So this times this is just 1. And then minus this times this. Sorry, plus that times that. Which is also 1. So that's just 2.
Yep.
Okay. And then we do this times this. Well, that's a little trickier. So that's negative e to the negative t. And then that's going to be minus 2 e to the negative t.
It should be a plus.
I have a minus sign here.
Oh, yeah.
Did I fuck up?
There's not a no. I forgot there's not a minus sign on the 2. That's
Okay.
all.
And then this is dt.
Yep.
And then what do? You integrate each thing and you get...
Yeah, you just integrate component wise.
Oh, okay, cool.
Because you could
Right.
imagine you could rewrite this right as 2i plus then your negative 3 to the
Sure,
negative
sure,
t,
sure.
j,
It's
and
just
then
components.
just integrate each component.
Okay. Oh, well, wait. So negative e to the negative t minus 2 to the negative t. That's just negative 3 e to the minus t, right?
Mhm.
Okay. So then the integral of that is just going to be 3 e to the negative t, right?
Yeah.
And then this is plus c, technically. Okay.
We don't need to consider the plus c in this case.
Don't need to.
Yep.
Okay.
And then, well, all we need to do from there is technically what we do is we call the whole right term, the phi times that integral we just solved, we call that u, which is our particular solution to the system. And
So
then we already know, and that's our particular solution. And then we already know our general solution from finding the eigenvalues and the eigenvectors.
Is that this part of the? Is this the front part?
Yeah, that's technically our
General.
Yeah, our general solution.
And this is our particular.
That's our particular. So what we can do is
What are the column vectors? What's that C vector thing? What's that?
Because it's a matrix, when we multiply through, we need that vector to be our constants that we would have in our general solution.
Okay.
So it's just a column vector
of the eigenvalues?
Constants. No,
just
constants. Yeah.
Oh,
just
okay.
Constants.
Oh, so you would just say, okay, so the full solution, right, would be our phi, which was this.
Well, so it's easier if, in this case, we don't even write phi necessarily. What we do is we just take our general solution that we would normally find from our eigenvalues and our eigenvectors. So our eigenvector multiplied times e to the 1t and then e to the 2t. And then we just add that right term there, which is just our solution to this integral multiplied by our matrix phi.
Okay, wait, so I still need the matrix phi, but then it's this. Right, because this was phi. Phi was this thing.
Yeah, that's phi.
So this times this is on the right side. This is our particular. And then our general solution was the vectors. Oh, so 2, 1, e to the t. Plus, I think it was 1, 1, e the minus.
And then e to the 2t.
E to the 2t, okay.
Yep. And then we also technically have our C1 and our C2 on the left two terms. We don't need the C3 on the right term though.
Okay. Cool. And that's it?
Yeah, that's it.
Wow. I don't know what math is involved there. Well, there's a lot of math, but it seems kind of just mechanical, right?
Yeah, somewhat. There's a lot more like theory that goes into it. Like,
yeah, I'm like, where the hell did this come from, dude? Where'd this come from?
Yeah, I was gonna send it, but it was like a solid, probably page worth of just properties about what phi is. But it comes from, we start by assuming that our solution vector, our x vector, is of the form phi of t multiplied by our u vector of t.
Okay.
And then we basically just take some derivatives and show that it's a solution, and then we can get our total solution from there.
So kind of like work backwards from it almost.
Yeah, in essence.
Nice. Crazy. Well, that was cool. I know how to do advanced differential equations now. Or at least one part. I know it felt kind of mechanical, but I do like getting stronger at being able to like find eigenvalues and eigenvectors. This is something I was miserable at, dude, in undergrad. I was so bad at it. I don't know why. It's so easy now. I'm like, man. And then
I wasn't great at it when I took DiffyQ, but I think they kind of like overcomplicated in whatever course I was in. Because I remember doing some like row reduced echelon form stuff and all that shit, and I hadn't taken linear algebra at the point. And I was like, I don't even know what to do at that point. And then I took this course. I was like, oh, whatever we're doing here is a lot easier than they were doing in normal DE.
Lucky Cat. Oh no, I missed a stream. Lucky Cat. Why'd you miss a stream? Lucky Cat, you know when we're streaming. We always have our calendar. Although I guess has been a little bit weird because I streamed earlier today with lecture and then did an hour of physics stuff, and now we did an hour of fun stuff. But don't worry, Lucky Cat, we'll still be on tomorrow. America said, my question from last time, how do we memorize this? Well, you don't really memorize. You don't memorize hex to binary. You have to know how to convert binary and to decimal, I guess, and then hex to decimal, and then just like link the two. You don't know how to convert? Okay, well we can do it next time. Sorry, you just submitted like a screenshot last time. That's not really a homework
There's
question.
actually a trick that you can memorize to do hex to binary and binary.
Yeah, I've seen it before. Yeah.
Yeah, you group it into 4s, and then whatever the value of that 4 binary digit is, right? Say it's 9, then the digit for the hex is 9, and then you do it for the next one and the next one, and so on and so forth.
Oh, interesting. Oh, I see. Okay. Because 2 to the 4th is 16. Right?
Yeah,
exactly. That's kind of why it works.
Yeah, and let's say you had like you wanted to convert to an 8-bit, you could do the same thing with groups of 3, and I guess technically you could do it with anything that's multiple of 2, or not a multiple, a power of 2.
Fascinating. I see. It's kind of like decimal, I guess. Yeah, kind of grouping and stuff. Can you reference a Goog YouTube video for the conversion? Maybe. Well, I'll let Brescos find one if he wants. But yeah, let's do that next time, America. Sorry, I'm out of time right now, but yeah, I'm down to do it. It's just I have to go. But alright, cool. Here, let's end on the stream. It's almost like it's fucking counting. Sensation, dude. Always hilarious. Alright, thank you everyone for coming to Actual Education Office Hours today. Appreciate all you guys with the questions. Thanks for being patient with me as I start teaching at UCLA this summer. It's gonna be a fun 6 weeks. If you want to learn some E&M, I know today's lecture was kind of like whatever, because an hour of it was just figuring out a syllabus. I have to explain all these things, otherwise I get like a gazillion emails because people don't listen or they don't read or whatever. But so we're gonna be doing some more interesting physics stuff in that class coming up, and then yeah, we'll have our office hours tomorrow as well. When is the next stream? Yeah, stream is so if you ever go to actualofficehours.com, which is where you should submit your screenshots. Yeah, I will say the one thing, yeah, if you want me to answer questions, putting stuff in chat gets ignored because the chat gets like so full of stuff. But if you put things in the queue, they'll get handled. But the streaming schedule is here. So these ones during the day, this is me teaching at UCLA, so you can't really ask questions during those, but you can follow along and learn, and you can still earn channel points for watching streams. But the next stream will be 6 o'clock Pacific time tomorrow. So that's 5 o'clock Mountain, 4 o'clock Central, 3 o'clock Eastern. Yes, I know you did, Merca. Well, Merca, you just submitted as a screenshot. You didn't ask like what. I saw a screenshot of like binary to hex, and I was like, okay, that's cool. Yes, just do that again. But at least this time I know you're asking a question about it. You're welcome, Jeff.
My name is Jeff.
Thanks for coming by the lectures, Jeff, too, as well. I appreciate you guys in Twitch making commentary. It's cool. I'll look at it as much as I can during the lectures. You guys do provide some interesting things. That tank question was cool, right? The tank and the heels. Yeah. But yeah, so check out the calendar. I'll be teaching physics tomorrow in the early afternoon. We'll be doing office hours later in the evening, and then it looks like Zach will have math and science help earlier if you need help. Go check out Zach's stream. Let me give me a little shout out. E to the 2I pi. Yeah, go check him out tomorrow afternoon. And Penn Center's also doing real analysis. Yeah, if you want to learn real analysis. And then it looks like Zach will be doing his E&M study group. So if you want to learn E&M kind of in parallel to what I'm teaching this summer, make sure to go check out Zach's study group that he's going to be doing on Thursday. Maybe I'll make a guest appearance after my stream to come say hi to him. But okay, cool. Let's go raid somebody. Let's go say hi to another streamer. Dun, dun, dun. Let's see. Who are we following? Who we can go say hi to? Oh, you guys can't see any of this. I need to reset my Explorer browser. Dun, dun. Let's go and say hi to Moo. I have not rated them in the last 30 days. Go say hi to Moo. Moo Hoodles is an awesome astronomy streamer. She does like astronomy news and stuff. I met her at TwitchCon, hoping that I can get Zach to come to TwitchCon this year. I'm gonna work on that with him. But anyways, enjoy the rest of your Monday. We'll see you tomorrow. Peace.
And that's what pisses me off. Yeah. Because then I have to go in and say, okay,